Okay. Let's take a look at the library of functions. So what do we mean by library of functions? In this section, we're going to give you some basic functions, some 8 total different functions that we will be working throughout the course with the algebra portion of this course. And these functions tend to repeat as you go to your calculus and above. These functions, we tend to keep them in our library. Think of it in your toolbox. So these functions we're going to use quite often in the future. Might as well talk about them now. And the way I'm going to do this is I'm just going to give you the function and the graph of the function without going through the details plotting their points. Okay. So for example, f of x equals b, where b is a constant here. Any constant you want it to be, including 0. So f of x equal to a constant, the graph of this function is going to be, suppose here's my coordinate system again. So the graph is going to be at the value of b. Now, depending on if b is positive, negative, or 0. So I'm assuming b is positive here, so I'm above the x-axis. And there you go. So graph of f of x equals b is like y equal b. It's going to be a horizontal line at the height of b. Now for these functions, we'll try to define the following, some of the characteristics that we are interested in. So this constant function, it is an even function, by the way. This function is even. Change x to negative x, you still get a constant. So the function is even. Let's talk about the domain of the function. The domain of this function is going to be all real numbers. That means b can be anything, all real numbers. Okay. And whatever b is, for example, let's say b is 8, then the value of function is always 8. Okay, so what is the range of the function therefore going to be? The range of the function is going to be actually just b. Right? So for example, if you look at this function, suppose this is b equals 8. The range of this function is 8. That means it's only defined at 8. Okay. And what else? Let's say for x, y intercepts. Again, I'm thinking all the key characteristics of a function we are interested in. The x-intercept, again, for this one is... well, there is no x-intercept unless b is 0, right? I'm just going to say no x-intercept unless b is 0. If b is 0, you get the entire x-axis. So the x-intercept is going to be all real numbers, right? Otherwise, there's no x-intercept. You can see this graph does not cross the x-axis. This is an oddball to do these for the constant function. The others are a little easier to go through. The y-intercept. What about the y-intercept? Well, the y-intercept is going to be at 0 and whatever b is, right? That was the easy part. And what about the increasing, decreasing, let's say? So the function is, in this case, remember, increasing has to be rising, decreasing has to be falling, and in this case, the function is neither increasing nor decreasing, it's constant, right? So increasing, decreasing, it's just going to be constant. It's neither. And what about the extrema? We talked about extrema in the previous section. Let's put it to work here. It means max and minimum. Well, every point on the line, on this blue line, will be both max and a minimum. So the extrema is going to be located at x and, of course, b. The value of the extrema, that is the maximum or the minimum, is b. So b is both max and minimum, okay, for a constant function. And that's good enough for a constant function. Our next function of interest to us is going to be the identity function, f of x equals x. The graph of this function is going to look, again, we're showing the graph of these in their most basic form, where they they don't have any constant, for example, multiplied by or added to or whatever like that. So there you go. And that's the graph of it. Here's x, there's y, and there's 0. So you're just going to get a line. F of x equals x is going to be a line. So for this one, again, let's go through everything. Domain is going to be all real numbers, negative infinity to infinity. The range of the identity function, possible y values, negative infinity to infinity. Right, y could be anything. There's always a y for whatever x you choose. Symmetry, when you change x with negative x, right, you get negative f of x. So that means this function is symmetric. WRTO with respect to the origin. Okay, so here's what that means again. Suppose this point xy is on the graph, then this point negative x and negative y would also be on the graph of the function. All right. And what else we have? So we talked about domain range. How about xy intercept? Well, for the identity function, x-intercept and y-intercept are both at 0, 0. Okay, the function is always increasing. As you go from left to right on the x-axis, you're going to climb on that line. So it's increasing from negative infinity to infinity. All right. And extrema. Well, there is no extrema. There's no extrema. Means there's no max, no minimum, because it extends in both directions forever. So there is no maximum y, so it just keeps growing, right? And by the same token, there is no minimum. It always gets smaller and smaller. And there we have the second of the 8 functions. All right, so first one was the constant function, and the second one was the identity function. Now, let's take a look at our third of the 8 functions. So let's go with f of x equal absolute value of x. The graph of absolute value of x is going to look like this. It's a V-shaped graph, right? So here's x and y. And the absolute value is actually made up of two lines, right? So this part, the positive part above when x is positive, this is actually y equal x. The other part of it is y equal negative x for x is less than 0. In fact, absolute value of x, if you recall from algebra, if not, there it is x for x positive or 0, and it's negative of x whenever x is negative. So we can actually write it as a two-piece function here, right? Which is piecewise defined, something we're going to talk about in a few minutes. So there's a graph of absolute value of x. So let's go through again domain range. Domain of absolute value. Inside absolute value, you can put any number for x, as suggested by the graph. X can be anything. The range, well, there is no maximum, right? The arrow points up, means y goes to infinity. However, there is a low point here, cannot go below 0. So the range is from 0 to infinity. What about the x-intercept? Again, x-intercept and y-intercept of this one are the same, 0, 0. That takes care of that. Increasing, decreasing. Well, it's going to be decreasing. The function is decreasing from negative infinity to 0. And it's going to be increasing from 0 to infinity. Oops, so let me use brackets. Remember, your author in the book uses brackets to include the points. As it's increasing, as x gets to the right of 0, gets larger and larger. Oh, symmetry. The graph is symmetric with respect to the y-axis. So f of negative x will equal to absolute value of negative x, which is negative 1 times absolute value of x, which is absolute value of x, which is f of x. So we got the original function back. Therefore, the function is even. And we can see that again from the graph that the function is symmetric with respect to the y-axis. And extrema. What about extrema? Well, I see a minimum on the graph, right, of this function. The minimum is 0. So extrema is going to be f at 0 is 0. This is a minimum. So there is a minimum of 0 happens at 0. Again, the x value is where the minimum occurs at. Just happens to be 0 again. And this one has no max, right? No maximum. Because again, the arrows go up forever, indefinitely. Therefore, there are no maximum for this one. And there you have it. That handles the absolute value function. Let's talk about the basic parabola next. Okay, so we're going to talk about x squared next. F of x equals x squared. Now for x squared, the graph of this, which we call a parabola, it's supposed to be symmetric. So there you go. That's what the graph looks like. The low point is 0. Let's go through our routine. Domain, all real numbers. You can put any x, square it, you get an output. The output that you get, which is in the range, is going to be the lowest point 0 all the way to infinity. So even if you put negative numbers, you square it, you get positive. That's why the 0 to infinity is indicative of that y cannot be negative. Okay, so we have domain range. Let's do our intercepts. Again, x-intercept and y-intercept of this graph are both at 0.00. Okay, and what else? Increasing, decreasing. Well, as we go from left to right on the x-axis, we go from left to right. First, the function is decreasing, right? It's decreasing, it means dropping from negative infinity to 0. And then from 0 to infinity, kind of like absolute value function, it picks up to the right of 0. And we did our domain range, the intercepts, increasing, decreasing, and symmetry. Of course, we do test for symmetry, f of negative x. That would be negative of x squared, which is the original function. And from the graph, we can see that this is an even function, right? Symmetric with respect to the y-axis. And so was the absolute value, right? Yeah, we called it even function up here. Perfect. The only other thing is extrema, right? For this one, let's do the extrema. For extrema, that means the max or the minimum. Well, I see a minimum. Min is 0 at x equals 0. And what about the maximum? There is no max. Again, the arrows indicate this thing grows forever. Just goes up to infinity on the y-axis. Cool. Got that one out of the way. And then next, let's take a look at cube. Again, this is why we call these a library of functions. So everything that I'm writing, we're going to take these to be known facts going forward. So if some problem involves graphing, for instance, f of x equals x cubed, you just say, yeah, that's in my library of function, and that's what the graph looks like, and these are the characteristics of it. So here's what the graph of x cubed now looks like. There you have it. There's clear symmetry with respect to the origin. That means if point xy is on the graph, so is negative x, negative y. And we'll show that in a moment. Let's go through our routine with every one of these functions. Domain, all real numbers. X can be anything. You can cube it, no problem. The range for this one also negative infinity to infinity. You can see y can go as low as it can, and it can go as high as it wants to. So those are the domain and range. The x-y-intercept, x-intercept and y-intercept again are 0, 0, because everything we're looking at are in their most basic form. That's why. Later this will change for us. They're going to be off center, off center of the number line, I mean, off 0, 0. Okay, increasing, decreasing. Well, let's see, increasing, well, the function as you go from left to right on the number line, see it's rising. So it's increasing from negative infinity to 0. And then it's decreasing from 0 to infinity. Actually, I'm sorry. It's never decreasing, huh? See, it's always going up. So it's never decreasing. All right. So it's increasing from negative infinity to infinity. I was still locked into absolute value and the parabola. So there you go. This function is always increasing. Interesting. So if you go from left to right, move your pencil on the graph, it's always rising. And even oddness. Let's do f at negative x. That would be changing x to negative x. When you cube negative x, you get negative of x cubed, right? That's negative of the original function. So therefore the function is odd, and you're looking at the symmetry of the graph, this graph, with respect to the origin. Good. We're done with this one. Now let's take a look at the one after. We're going to look at the graph of f of x equal 1 over x. The graph of 1 over x actually has two parts. Here's one part, and here's the other part of it, which is the mirror image of the right branch. The graph is commonly known as the oblique hyperbola. Let me write that for you. Oblique hyperbola. Near the end of the course, we will talk about conic sections, analytic geometry, and we talk about conic sections, and that's where you will see this again. So there's the oblique hyperbola. So let's write this one. Domain. It's going to be everything except all x's except 0. See, at 0 there is a vertical asymptote of the graph. Means there's no graph. So x is good from negative infinity to 0 union 0 to infinity. And you can try, when we put 1 over 0 for x, we get undefined, right? And that's the whole purpose of domain. What can I plug into this function? Anything. I can plug in anything but 0. The range is likewise the same. It's from negative infinity to 0 union 0 to infinity. For the range, again, you can see y always exists, except at 0 things kind of blow up. And x-intercept is going to be none. It's not going to cross the x-axis anywhere. Y-intercept is also none. So no x, no y-intercepts. Okay. And what else? We talk about increasing, decreasing. So now remember, for increasing, decreasing on the x-axis, we go from left to right. You move your pen, your marker on the graph. So it looks like the function is dropping, right? So I'm just going to go decreasing first. As I go left to right, the function is decreasing from negative infinity to 0. Now, to the right of 0, to the right, it's still decreasing, isn't it? Dropping. So this function is always decreasing from 0 to infinity. And there you have it. What about the extrema? Minimum, maximum. Well, it shoots up forever. There you go. So no max, goes down here forever, negative. no max, no minimum. So none. There is no max and there is no minimum. Good. Even oddness will clearly look symmetric with respect to the origin, right? So let me do f at negative x. That will be 1 over negative x, which we can write as negative 1 over x, right? Just bring negative in front of the fraction line, and you get negative of the original function. Well, that's the very definition of an odd function. F of negative x equals negative f of x. We did that in the previous section also, previous lecture. All right, the function is odd, and it wraps up this one. We're done with this one. Now, let's take a look at, we only got a couple more, right? I promise we will do 8 of them. Let me count how many we got so far. F of x be 1. That's 2. This is 3, 4, 5, 6. Yep. So I got 2 more to go. Okay, this next one, we're going to go f of x equal square root of x. Now the graph of the square root of x, again, without plotting any points, this is what the graph of the square root of x looks like. Actually, let me do it like this. There you go. Square root of x. That's x, and there's your y coordinate system. Here's 0. Notice square root of x was only defined for positive values of x. That's when the radicand is positive. So here we go. Domain is going to be from 0 to infinity, including 0, because the square root of 0 is 0. What about the range? The range is also from 0 to infinity. But for the range, again, we're looking at the y values, right? Up here. So if you can see these project, of course, it's going to take a heck of a lot bigger x, right, to create y, make it go a little higher. But eventually, at snail's pace, but eventually it works its way towards infinity. Okay, so we got the domain, the range, and what else do we want? The intercepts, right? Well, we are back to x-intercept and y-intercept, both at 0, 0. Anytime x is 0, naturally y would be 0. So the xy intercepts become the same. Increasing, decreasing function. Well, as I go from left to right on the number line, I'm always going higher on the graph, right? So therefore the function is always increasing over the entire domain from 0 to infinity. And it's never decreasing. What else? We got increasing, decreasing, even oddness. Well, let's check it out. Let's do f of negative x. Well, f of negative x would be square root of negative x, and that clearly does not equal to the original one, right? So the function is not even. There is no symmetry with respect to the x-axis. Now, what does negative f of x look like? Well, negative f of x is negative square root of x, right? And since the square root of negative x is f at negative x does not equal to negative root x, so this function is not odd. Therefore, up here, not even. Down here is not odd. So this one is neither even nor odd. And you can see the graph. There is no symmetry in the graph. And by the way, this part, this is, some of you may say, well, no, that's not right. Square root of negative x, I can bring negative outside and it becomes that, right? Well, nope, we can't do that. You're not allowed to. Part of the reason is this: when you look at sidetrack here, when you look at negative x, I can write it as negative 1 times x, right, for this one. And this one would be like square root of negative 1 times square root of x. So you got this part correct, but this part is incorrect. So you see that the square root of negative 1 does not equal negative 1. And if you recall from way back when, square root of negative 1 is that infamous imaginary unit, remember I? So for that reason, I don't want to get ahead of myself here, but there you go. So this is not even nor odd, neither. Oh, extrema, the last thing. What about the extrema of this function? Well, the lowest point is 0, right? The max, there is no max. So extrema, I'm just going to say no max. And there is a minimum, right? Minimum is 0. The value of the function, by the way, is the minimum, not the x value. But extrema is 0 in this case. Where it happens is at x equals 0 also. All right, and the last, not the least, would be f of x is equal to, this is the 8th function in our library of function. And our library of function, by the way, will only grow as we go forward, right? Remember, these functions, you're welcome to use it after this lecture, on our future lectures, and in your higher level courses, in your calculus, differential equations, and above. Your instructor does not expect you to plot points for these. They expect you to do them exactly like I am doing them. Just be able to graph them without any plotting points. Now the cube root function is kind of like the square root function. Let's say this was a square root function, right? There is a subtle difference between them. It's actually closer to the y-axis initially. Okay, so this is what the graph of cube root of x is going to look like. That's cube root of x. Now remember, the domain of a square root function was x had to be positive because square root of negative numbers were not real. Well, in the case of cube roots, negative numbers are okay. So for instance, cube root of -1 is -1, because -1 by -1 by -1 is -1. So this is doable. Cube root of -8, for example, is -2. Why? Because -2 times itself 3 times gives you the -8. Therefore, that would suggest that there's also this other portion of the graph of this function, right? It's not just limited to the first quadrant. So I'm just going to draw this part of it also, right there. And that is the graph of cube root of x for us. Okay. And we're going to go through our routine. So let's go with domain. What all can x be? Anything. Even negative numbers in the radicand are fine. What about the range? Well, the range can go from -infinity to infinity. Again, it's a kind of very slow, painful, gradual rise, but eventually it will get there ultimately. The range domain intercepts. Okay, for this one, again, x-intercept and y-intercepts are both the same at 0, 0. The function, as you go from, again, left to right on the numbered line, you see this is always increasing, right? So the function is increasing from -infinity to infinity. And last not the least, the extrema. Well, it's always rising, right? So there is no max. Correct? As x gets larger, as x gets smaller, it's always dropping. So none. There are no extrema of this function. Perfect. So we've got all 8 functions covered. So again, going forward, feel free to just cite the graph of these, and that's what I will be doing. I say, well, remember the graph of cube root of x look like? We're just going to graph it without plotting points. Now, let's finish this work with piecewise defined function. So what do we mean by piecewise defined function? Okay, that's our last topic. Piecewise defined functions. Piecewise defined functions are really just that. They're pieces of functions. They're made up of 2 or more functions. So one piece is a function, another piece a different function. So for example, let's say I want to graph f of x equal to, using something we have done, the library of our functions, 3x minus 2. Oh, 3x minus 2, by the way, is a linear function. The linear functions we talked about earlier. Okay, so let's see how this is going to go. Now, I have 3 functions here, but each function is only good over a certain domain, okay, x values. And let's say the last piece is good for when x is positive. So I have 3 pieces of this function, right? So let's say we want to graph the function in here. Okay, so let me bring my coordinate system first. Okay, so here I have my Cartesian coordinate system. Let's actually graph these. The first piece we're going to graph, again, on the number line, we're going to go from left to right. So the first piece is going to be for negative x's. So we're supposed to only look at that. Okay, now we know what the graph of x squared looked like, correct? That was in the library of functions. Remember, it looked like that? Well, the negative x squared is going to reflect it, right? Downward. So I'm just going to graph this thing like so. Okay. However, this graph is only good for negative x's, right? So I don't need really this portion of the graph, do I? Because this is only good for negative x's. So I went ahead and removed that portion. You see how that works? So that's the first piece. Now, when x is 0, exactly 0, the value of the function is at 4. Okay. And let's say this is where it's at. That's at 4. Okay, notice I have a single point. And for positive value of x, I'm supposed to look at the graph of 3x minus 2. Now, the graph of 3x minus 2, this one, is going to be a line, right, whose y-intercept is at negative 2, slope is 3. Isn't that what the graph looks like of that linear function? True. But only for positive x's means we don't need this part of it. This is only good for positive x values. So I'm going to go to a negative 2, and I'm just going to graph this line. And there you go. That's going to be the graph of this piecewise function. Notice how quickly, by the way, I graphed this line, 3x minus 2. I started at y-intercept, negative 2. Rise over run. Slope, 3 over 1. So we go 1, 2, 3 up over 1. Right? 1, 2, 3 up over 1. That's the second point, and just connect them. So that's how you can graph these without plotting points. And there you go. We're done with that piecewise function. It wasn't so bad, right? And there we have that one. Let's try, how about another one? Let's do another piecewise function. Let's do one for two different kinds of functions. Suppose, let me make one up. Let's say this time, I'm going to make it fancier. F of x, we're going to go absolute value of x on one, and we're going to go x cubed for the other. Again, both of those are in our library of functions. And this one, I'm going to make it good for x between negative 2 and 0. Okay, excluding 0. And x cubed for x greater than 0. Notice 0 isn't a value here. I have not included 0 in there. Okay, let's try this and see what happens. Again, let me bring my coordinate system first. All right, so I have my coordinate system. Let's do absolute value of x from my library of functions. Again, I know my absolute value function is going to look like this. That's over the entire domain, negative infinity to infinity. However, this is only good from negative 2 to 0, means from, let's say here, call that negative 2, up to not including 0, right? So I actually have an open circle at 2 here. Okay, right in here, I have an open circle at 2. Therefore, that portion of the graph, and when x is -2, y is also 2. So that's what this part looks like. I'm going to put a circle there, right? That point is when x is -2, absolute value of -2 is 2, so that's going to be actually a +2. There, that's what that is. This part of the graph, this part we don't need, because that's the graph absolute value only when x is less than 0, between -2 0. And it's important, notice I have an open circle at 0, means 0 itself is not included. Now, the graph of x cubed, what does x cubed look like? Now, if you remember the x cubed in our gallery of functions, what did it look like? It looked like so. There it is. You can remember this one? That was the graph of x cubed from our library of functions. So what I'm going to do is I'm just going to draw, and 0 is not included, right? So again, I have an open circle at 0, and it goes the right side. Looks like this part, and the left side, which is that, we don't need, correct? Because that's not part of the domain. Only for positive x's it's gonna look like x cubed. And there we have it. You're looking at the graph of this piecewise function. Notice that you have arrow on the right side, the left we do not have an arrow because we have equal to, which kind of terminates it at that point. And there you have it. So the functions could be different, but the process is the same process. You could be doing cube roots, square roots, and so on and so forth. Maybe I'll finish this one with, how about, let me make one last one up. What about this one? Let's say f of x is going to be, I'm going to go square root of x for x greater than or equals 0, and I'm going to go cube root of x for x less than 0. Okay, this isn't going to take long to do at all. Check this out. Remember, square root of x look like this, right? That's root x. Now, the left part, right? The left part's going to behave like cube root of x. And remember, cube root of x look like that. I don't need the right side of it, true, because x is less than 0. So there is a graph of this one. Now, there is a hole where 0 is for the green, but then that hole is filled out by a square root. So that gives the idea of continuity to the graph. So the final graph, there is no hole at origin at 0, 0. Okay, and there you go. We're good. So hopefully you're able to follow this. And with that, we are done with this lecture. Again, thank you for watching always.